Welcome back. In part 2, we're continuing with the example that we were looking at in part 1. At this point, I'd like to summarize what we found out so far. We solved for the force F1 in member 1, 37.05 kilonewtons. I also will give, without proof, the reactions C sub x and C sub y, which we know how to solve. And we can find the resultant by taking the square root of the sum squares of the components. And interestingly, and perhaps you could have guessed this, is also equal to 37.05 kilonewtons. If you'd like to, pause the video and try that on your own. That would be a good exercise. But now to the important part that we are really interested in, solving for the stresses. Okay, so first thing, the stress in member 1. Once we know the force, solving for the stresses is very straightforward. Remember, the formula for stress is simply the force divided by the area. The most important thing here is that we get the right area, and there are a few defined in this problem. For member 1, we want the area of that member. Okay, so we're going to take the force in member 1, 37.05, multiply by the conversion factor of 10 to the third. That gives us the force in newtons, and divide by area 1, which was given as 3,000 millimeters squared. This is newtons per millimeter squared. My answer will be in megapascals, and I get 12.35 MPa. Okay, so that's one of the answers I'm looking for. Next, how about the shear stress in pin A? We already said that the force, the shear force that passes through pin A, which I'll call V sub A, is equal to the force F1. The shear in pin A, tau sub A, is equal to the shear force divided by the area of the pin. Notice this is different than the area of bar 1. The shear equal to 37.05 times 10 to the third newtons, but the area of the pin comes from the diameter of the pin. And we can calculate that as pi over 4 times 30 squared, which is the area of a circle with units given in diameters, and the units are in millimeters squared. So again, newtons per millimeter squared. This will give me an answer in megapascals, and I should get 52.4 megapascals for the shear in pin A. Okay, finally the shear in pin B, pin C. Shear in pin C. We said since it's in double shear, is going to be equal to the force passing through reaction C, which I called C, divided by 2 times the area of the pin, because the shear is passed through 2 different locations. Notice that this is exactly equal to half of the answer we had before. We can write it out to be thorough. 37.05 times 10 to the third newtons divided by 2 times pi over 4, 30 squared millimeters squared. So this gives us half of this answer, which is 26.2 megapascals. And this is the area of the pin C. Okay, some quick logic checks for problems like this. We would check to make sure all our stresses are in the correct units, and since we were thinking of that the whole time, we managed to get this right from the beginning. We might also check the magnitudes of the stresses if they make sense. The stresses in the pins are higher than the stress in member 1, which makes sense because pins tend to have smaller areas, so the force will concentrate over those areas, giving them larger localized stresses. The other thing we might check is that all of these stresses are within the yield range of the material. A typical yield stress for an engineering material starts at about 200 to 300 megapascals. So usually stresses do not go into the yield range, and that is true for this particular problem.